Well, this is the video solution for exam 2. Problem 1 was a conservation of energy problem, as I've described here. And what we're looking for is that if there is no friction, which is kind of a key thing, if there's no friction, then mgh at the top equals 1/2 mv squared at the bottom. We can write the full energy equation of T1 plus V1 plus U naught is equal to T2 plus V2, or we can just write mgh is equal to 1/2 mv squared, in this case for conservation of energy. And the distance is the height here, which is 120 minus 10. So that's what we're looking for, and we can solve that for 84. What we went through in class a couple of times is that it doesn't matter how steep this angle is. In other words, this angle could be shallow like that, or it could be very steep, and the speed at the bottom is independent of that angle. So in other words, that angle doesn't matter. And that's what I was looking for there. All right, and this one was another conservation of energy problem. And what we have to recognize here is that, again, if it's frictionless, which is key in this assumption, is that it doesn't matter how steep the path is. It could be a shallow path or a very steep path. It doesn't matter what the weight is. The weight can be heavy or large. But if there is no friction, then the speed at the bottom is going to be the same. So that's what we're looking for. Which one has the most speed, and they're going to be the same. Now, which one gets to the bottom first depends on the length of the path. In this particular problem, I had this one at a shallower angle than this one. So this one has a steeper angle at 60 degrees, so it's going to get there fastest. If this one had a shallower angle like that, then it would probably get there slowest. So the time is not the same as the speed at the bottom. So in terms of the way we look at it, we look at the distance of the length of the path, or how fast it can get there is going to depend on the length. So the speed at the bottom is an energy problem. The time, we can solve that with F equals ma or energy, but the main thing is, F equals ma or momentum. I solved this with momentum here. You have to recognize that the acceleration down the hill has this sine component. So F equals ma down the hill would be that sine component. So we've already done a few inclined plane problems. We're going to do a few more. And as I warned the class in class, enough people miss this problem that I will give this again on the final exam. So look forward to having some sort of an inclined plane problem where you have to find out the time at the bottom on the final exam. Now, it could have friction, though. So this one was a frictionless one, so be prepared to solve for one with friction, or maybe a stepped problem. Maybe it has a shallow angle for a while and then a steep angle, or maybe a steep angle and then a shallow angle. All of those are very easily done, with either F equals ma or momentum if we're looking for the time. Okay, second problem here was a conservation of momentum problem. Needed you to recognize that with impact at where the coefficient of restitution is equal to 0, special consideration applies, and that means that the conservation applies in both x and y. So all we had to do is sum the momentums in x, and we know that if the E is equal to 0, then they exit with a common speed, and the masses stick together. So the exit speed is going to be a common speed, and the masses are going to be pulled together. So again, we have beginning momentum from particle A, and beginning momentum from particle B in the x direction. If that's the x direction, it was given on the drawing. We can find the exit, do that equation there. We can't solve for anything yet, so let's look at the y equation. The y equation, we have momentum in the y direction from particle A, but no momentum in the y direction from this guy. So this one we can solve for velocity A with that. With this speed here, and we substitute in there, and then we can find the speed of B. So again, the takeaway here is when E is equal to 0, they stick together. They have a common speed at the end, and that's what we were looking for in the main part of the problem. All right. This guy, conservation of energy problem. Again, no friction. Didn't have to solve for friction on here. But we did have to recognize this as an NT problem, and NT means that there's normal force along the path. circular motion of these kinds, or it doesn't have to be circular, it can be a parabola, it can be anything, where we did a normal force. But what we're looking for here is that it has to get all the way to the top without losing contact. So that without losing contact means that it's going this way, and if it loses contact, it's going to become a projectile. We did a homework problem like that. But that doesn't mean the velocity goes to zero. The velocity is not zero. It still has some speed. In fact, the speed at the top is what allows it to stay on the path or stay connected to this circle thing here. So free body diagram is required, and that's what we're looking for, is right up here at the top. We know that there's a speed at the top. The key dynamics talk here is that without losing contact means that we're looking for the place where the normal force goes to zero. So normal force has to be going, holding it on the path. Got an mg in this case going straight down. Got a velocity. I'm looking for this free body diagram with the normal force pointing in the correct orientation or the correct direction, pointing in toward positive normal is going down. Then I'm looking for this equation, sum of the forces in the normals, mass times acceleration normal, where the normal force goes to zero. When you do that, you can solve that for the velocity to stay in contact, and now it's just a straight energy equation where you have T1 plus V1 plus U naught is equal to T2 plus V2, and if the datum is at the bottom, I guess I didn't call that out on the picture here, but that's what I was saying, that the datum's on the bottom. So as the energy is released from the spring, 1/2 ks squared in the spring, we have to climb up to the top. We'll have an mgh and a 1/2 mv squared at the top. I've already solved for the proper velocity at the top, sorry about that, and so I can solve for the spring energy looking there. All right, problem 5. This was a recoil problem, or at least it starts as a recoil problem, and what we need to take away from all those examples we did was that in all recoil or skateboards or barge problems, it starts, well, no, I shouldn't say all, but in general they start with zero momentum, zero linear momentum, and then when the explosion happens or when we jump off the skateboard or whatever, one thing goes the other one way and the other thing goes the other way, and that's what instantly happens when we have recoil, like a cannon shooting a ball, a projectile, or a gun or something like that. It happens instantly, and we immediately have a velocity of the ball and we immediately have a velocity of the cannon. Now what happens is, now that the velocity or the cannon has a velocity backwards, that's the first thing we're looking for, is what's that instant velocity. And then we recognize that it's going to be sliding relative to the cart. And then it's like the suitcase on the cart problem that we did in homework. And it takes a little while for it to slide relative to the cart. And then it sticks to the cart and the cannon proceed to the left or to backwards with a common speed. So that's what I was looking for. The speed of the cannon immediately after the shot, and then the final speed of the cart. And we'll start this problem with a momentum, conservation of momentum, that we start with zero momentum, and then we have a mass of the ball times the velocity of the ball, mass of the cart, or excuse me, the mass of the cannon, I called that particle A, times the velocity of the cannon. Whoops, that should be a velocity of A, not the velocity of C. So don't get confused here. That should be mass of A times the velocity of A. I put it right here, but right here I put those should both be VA. We also have to do a relative equation, so we're going to say the velocity of the ball is equal to the velocity of A plus the velocity of the ball with respect to A, and that B with respect to A was given in the drawing. Where is that? It says that the cannon fires the shot 500 feet per second relative to the cannon. So that's what that 500 is. You plug that in there, and again, those should be A's on that. All right, now that the now that the cannon is moving, we have to find out what the new speed's going to be once they stick together. And we do that by saying that we now have an initial momentum of just the cannon. Once they stop sliding relative to each other, we're going to have a total momentum of the cart and the cannon, which is going to be equal to the beginning cart and the cannon. So I'm going to say that we have a MAVA, which I just solved for. Now, when they stick together, I'm going to have the common mass of the cart and the cannon together, and I need a new velocity, and I can solve that for 7.28. Now, the hard part here was this question up here. The harder part was during the time they're slipping, how far do they go? What's the distances? And we did a couple of problems like this where we had to solve for distances using energy. And so what we're going to say is that the energy of the cannon has a 1/2 mv squared as soon as I fire the shot. It's going to slow down over some energy, and it's going to end up with that speed. So I have that for just the cannon, I have a 1/2 mv squared minus a friction times a distance is equal to an ending 1/2 mv squared. And if you look at the free body diagram, we have a beginning speed. The friction force is actually going to slow it down, which is why it's a negative. If I define the left as positive, I just did that for convenience because everything's going to the left. It's going to have a beginning speed. Friction force slows it down, and I can solve for this, the distance that the cannon moves during the time that it goes from the beginning speed of 14, the ending speed of 7.2. Now the cart, what happens to the cart? The cart has an initial kinetic energy of 0 because it's not moving. But what's making the cart go? Well, again, if this is a positive force in this direction, as we said, positive in that direction, if I take that friction force slowing the cannon down, that has to transfer equal opposite to the cart, and that's what makes the cart speed up. And again, in the end, the cart is going the same speed as the cannon. So it has that same friction force, that equal opposite friction force, and I get that, and I get the distance that the cannon moves throughout this whole process as 1.6, and then the distance the cart moves relative to the cannon is the difference there. And then the last problem is the maximum speed question. We did several of these in class and in homework. Several ways you can go about this, but probably the easiest is to find, in this case it's a momentum problem because the tension here in the string driven by that motor is a function of time. So if we set the total forces here equal to mass times acceleration, which is equal to, again, where acceleration is equal to 0, where acceleration is equal to 0, that's where we can find the time for the maximum speed. Plug that tension in there. It's got an mg sine theta going down here. It's got a force of friction pulling it up the hill, and I can find that time. And then I plug that time into a momentum equation. And the momentum equation starts with the beginning momentum. I have a mv. I have all those forces I have to put in there. And this is what a lot of people did wrong, is they forgot one or two of those forces, or they forgot to integrate it or something like that. But these two forces are constant, so they just have to be multiplied by that time. This one has to be integrated because it has a function of time. And when you integrate this and multiply all these things out, you get the final speed is equal to 5.01, if you will.